All right, so picking up right where we left off the other week, we were in the box engine module. Couple functions left to go. We covered the calc function, which was the heavy lifter, which does really the box layout computations for us. There's one left, which is the adjust function. So this is I kind of want to call it a method, but it's not a method. It's just a function in the namespace called box engine. But this is a function which is called to adjust the sizer by a delta and update its neighbors accordingly. So probably somewhat of a visual explanation is a bit in order. So let me do this. Okay, so this is this example here is just the data grid example that we have online, just a bunch of data, but internally it's using the box engine to do things. So if you notice, as I resize this, the actual browser window, the sizes of the panels change. So that's under the hood. It's calling the box engine.calc function to do that layout and proportion the space appropriately for all what is this, 5 panels. But what happens if I want to just move or resize one of these panels in the middle? So this is where the adjust function comes in. So what the adjust function allows me to do is basically tell the box engine, hey, you've got these particular box sizers. They're in a row and they have their current size, and I just want to adjust, let's say box sizer with index of 1 in this case, and I want to grow it by 10 pixels. Well, sometimes it's possible to do that, like I am right now. But as I get closer to the edge of this and I start to hit the minimum size of this box sizer over here, all of a sudden I don't have room to expand the one that I want to without adjusting the other ones. And so if we see here, as I continue to move this, all the other ones start adjusting their size as well. That's what the box adjust function does for us. It gives us this really nice resizing behavior where I can resize it as long as I don't hit limits of something, and then as I hit limits, the other panels themselves start to resize to take up that space that I'm asking for. So this is one of those prime examples of a layout that is simply impossible to achieve with CSS. You can't get that behavior. You have to do it in JavaScript. And so we do it in JavaScript, and that's what the box engine adjust function allows us to do. So that being demonstrated, it's a fairly simple function. You just give it the array of sizers, which are currently sized how you want them, the index of the sizer you want to adjust, and then the amount of pixels you want to adjust it by, either positive to grow it or negative to shrink it. What that means is that there's no difference here from me, trying to grow box sizer in index 1 when I move this splitter to the right, or shrink the sizer at index 2. They're more or less equivalent operations. So that's this function. It does some quick logic to check if it can bail early. Basically, if there's nothing to do, then it does nothing. Otherwise, it calls into these private functions to either grow the sizer at a particular index or shrink a sizer at a particular index. So those two functions, these are private functions. You can't call them from outside the module. They're exact inverses of one another, so I really only have to cover one of them. The other one is literally the same logic, just inverted to shrink a sizer instead of grow a sizer. So the first thing that we do, if we're going to grow a sizer, then that means we have two things that we need to consider. We need to see how many items that are to the left of the one that we want to expand, how large that those can get, and we need to compute how much the sizers to the right can shrink, because we have two limits we need to deal with: the minimum size of the sizer and the maximum size of the sizer. So what that means is that if I try to expand this item right here and I hit its maximum size and I'm still trying to expand it to the right, then the ones that are on the right should shrink and the one that is on the left should expand in order to get that mentally logical behavior. And so the adjust function takes care of all of that internally. You don't have to worry about it as the author. It just does the right thing. That's why we need to compute both the grow limit and the shrink limit. And then we clamp the delta to those limits, because if we run into a certain amount of limits, for example, let's say that this panel can only grow to be 100 pixels wide and this one can only grow to be 200 pixels wide, then the maximum I can grow this may be like 300 pixels or something like that, and then I literally can't move it anymore because I've hit the limits, the maximum size limits of these two. So we definitely have to bound the requested delta by the amounts that we can actually adjust that sizer. Once those are computed, we basically just apportion that space linearly across the siblings in order. So we basically say the one that's closest to the thing that we're adjusting will take up all of the space if possible. If it hits its limit, then it gets applied to the next sibling. If that once that hits its limit, it gets applied to the next sibling, and so on. So that's where we get that chain reaction behavior that comes from these two loops right here, where we apportion the growth space and then apportion out the shrink space. So that's a pretty simple algorithm. There's no stretch factors or anything that go into it, so we don't have to do any of the ratio computations like we had to do on the calc function. It's pretty much just a straightforward distribution of computed space in a linear fashion. Any questions on that?
Chris, where can I find that demo that you were just looking at?
Yeah, so it's phosphorjs.github.io/examples/datagrid. Cool. Yeah, and I guess just a little, explanation. This is just demonstrating the performance of the data grid. So on this one panel right here, this is a trillion row by a trillion column data grid that I can scroll through in real time. So you can actually go through and count the rows if you want. You'll be there a while, but it is a full trillion by a trillion data grid, and all the columns and rows are interactively resizable. We've got an example of streaming data here, which is just randomly adding and removing rows. All this is fake data. It's just all generated client side, but it's really just to show the data grid. So we got an example of throwing JSON data in a data grid, as well as, let me kind of combine all these things together. We also have an example of shading the background colors of cells based on the value that's in the cell. So basically it's a heat map. It starts out as a heat map, but then as the data values start to randomly change, you get to see random updates. Then if you're actually to put on your, turn on your Chrome developer tools and see what areas of the screen are painting, I guess it's going to show you that this particular whole canvas is painting, but really in the canvas, the only thing that we're painting is the actual cell that's changed, which is why you get the real-time scrolling performance that we have here. Nice little tangent. The data is not done yet, but we're still working on it. Should ramp up here on development on that pretty soon.
Chris, question. At the time you wrote this, the CSS grid spec was not finalized or implemented. Can you do, so you showed an example of the logic that wouldn't work, presumably with Flexbox. Do you know if that resizing logic could be made to work with CSS grid?
I don't think it will. You could probably do it with some of this stuff by interactively adjusting the size bases of the stuff in CSS, but it's going to be way more expensive to do it that way, because anytime you make a write to that style sheet, you're going to do a full relayout of the page. So it's definitely going to be more expensive to do in CSS, no matter how you cut it. Okay, so moving on. So now we've talked about widget and layout and how those two classes are related. We talked about panel and panel layout, how those two classes are related. Now we talked about box engine, which is the underlying math engine, if you will, math module that powers both the box layout and the split layout. And if we recall from the convention, so we've got a box layout, which means there's going to be a corresponding box panel, which is kind of just a layer on top of box layout, but all the logic happens in the box layout. So this layout, I don't know. I'm trying to think if we use it in JupyterLab. Yeah, we do. So at the very, very top of the hierarchy, I believe there's a box layout, which is in the vertical orientation, which holds the menu bar at the top, and then the main panel, which gives you it's a panel which holds the left sidebar and right sidebar in center dock area. And then I believe there's also a hidden panel at the bottom that we're going to use for the status bar eventually. But that's all held in a vertical orientation box layout. So, okay, so a box layout, it extends the panel layout. And if we recall, when we went and looked at the actual panel layout class, it was designed for subclassing, which we've done here. So let me just bring that back up so I can refer to it. Okay, so if we recall, the panel layout itself had a few protected methods that we called into when we implemented. So we implemented a bit of the public interface that was required by the abstract-based layout class. And then a lot of that logic was that where we filled in a lot of these methods, a lot of that logic was basically shunted into calling the 3 protected methods: attach widget, move widget, and detach widget. And this is logic related to adding and removing child widgets from the layout, not logic which actually positions the widgets on the page. In the panel layout, that's assumed to be done all by CSS, and so there's no logic that's needed for that. In box layout, we're going to see where we can take control of the actual layout and do the layout in JavaScript itself. So the first thing we do, we've got the constructor for the box layout, follows the same pattern we do everywhere in Phosphor, where if there's ever going to be options that are passed to the class, it'll take an options object as a single argument, because that's a more extensible pattern than using positional arguments. So it takes its options, immediately calls the superclass constructor so that the base classes can initialize themselves, and then it goes through and parses the options that may or may not be included. So pretty straightforward. A box layout can have a direction, whether it's top to bottom, left to right, right to left, bottom to top. You've got those 4 direction possibilities. We'll see those later. You also have some alignment possibilities, which controls, it controls, let me see what verbiage to use here. It's the alignment of the widgets in the layout direction. The alignment has no effect if the widgets can expand to fill the entire box layout. So let's imagine, for example, that you've got a box layout and your direction is left to right. So you're positioning your widgets, your child widgets in a row. And each one of your child widgets, there's 5 of them. They've got a maximum width of 100 pixels. So the maximum that space that those widgets can occupy is 500 pixels. Well, if your box panel, or your box layout in this case, is allocated more than 500 pixels in width, and you've got an alignment set on it, then you've got extra space that needs to go somewhere between those children, and it kind of go to the left, to the right, or between them, depending on what you set up there. We'll get to what those options are a little bit later. It's got a dispose method. So again, the responsibility of the layout is to actually dispose of its contents and dispose of its children if necessary, which in this case, the base panel layout class itself disposes of the child widgets, but the box layout class itself uses a thing called the layout item. I showed that in the when we talked about the widget class and the layout base class. There was also a layout item class in those modules, which helped us do absolute positioning of widgets. There we go. So in the layout module, there's this layout item class. It's an object which assists with the absolute layout of widgets. And since the box layout is going to position its child widgets with an absolute layout, it uses instances of this class to wrap its child widgets to do all of that convenience, basically perform all of this absolute positioning logic for us, with the layout not having, where we don't have to repeat this logic basically in every single layout class that we build, and we just we can reuse this class. So what we notice is that when we dispose a layout item, it doesn't dispose the child widget because that's already being done by the layout. But what it does do is it resets the absolute, basically resets the style of the widget. Since the layout item is going to take control of that widget node and convert it to absolute layout and control all the styling information related to its position on the page, when we dispose of the layout item, it makes sense to undo that information, so it resets the widget style as appropriate. So that's what's going on here when we iterate over these layout items and dispose them. We're not actually disposing the child widget itself, we're just resetting its style. The parent class is going to dispose of the child widgets when that gets called, which is, as we saw, done by the parent panel layout. Okay. Then we had a couple of getters and setters for the properties of the box layout. So again, box layout has a direction and a box layout has an alignment. And if we need, if any of those ever change, we do a couple checks first. We check to see if the user's not actually changing the value. We do nothing. Otherwise, we update our internal state. If we don't yet have a parent widget, we do nothing because there's nothing to do yet. Otherwise, we update the parent's data set with a direction value. The reason we do this is that it allows, if you've got certain CSS styling, or you want to, let's say you want to style your child widgets, which are children of a box panel that has a particular direction in a certain way, and you want to do that with CSS, this allows you to do that. So one of the things we try to do in Phosphor is either, obviously we try to tag all of the classes with appropriate class names. We see that in every widget subclass. We do an add class with the name of the actual JavaScript class, so you know where it came from. That allows you to build up CSS selectors based on class names. This pattern here allows you to build up CSS selectors based on the state of a particular instance of that class, or multiple instances of that class, if you will. So we're trying to basically tag the DOM nodes with information that downstream users may find relevant for their use case, for either uses in CSS or for querying the DOM for nodes of a particular, which match a particular selector. So this is why that this data set right occurs right here. So we're tagging the parent node with the data set, and then we're telling the parent to fit itself, because we have to do a full relayout of all of the children, and we might have to update the parent's computed minimum and maximum sizes if that's requested, because if you're changing the direction, you might go from a horizontal layout to a vertical layout, and obviously your minimum computed sizes are going to change based on that. And then we have getters and setters for the box layout alignment. The setter is the same kind of logic. First, we check to see if it's a no-op. Otherwise, we update our internal state, then update the data set, and then we can tell the parent to update itself. Notably, the difference here between when we change the alignment, all we have to do is update the parent, versus when we change the direction, we have to fit the parent. And so the difference there is that when we're updating the parent, the layout will process that pending update request message, and it will simply relay out the children to redistribute the already existing space of the parent. It doesn't change the minimum computed size of the parent, because we're not actually changing the orientation of the children or the direction that the children are laid out. We're just saying that if we've got an extra space that's allocated for the children and they're not taking it up all of the way, we're just changing where within that space it's allocated. Versus when we're changing the direction of the layout, you might actually physically have to change the minimum computed sizes of the parent widget. So that's why you see you got to fit when you change the direction, but you have to update when you change the alignment. So it's a very subtle difference, but it's important. Then we got a getter and setter for the spacing. So this is the inter-element spacing. So let's say you want a box layout and you want 5 pixels of space between each of your children. You can set that with the spacing. Same logic there for determining if the thing is actually changed. And you also have to fit the parent in that case, because if you add 10 pixels of space between all of your child widgets, you have to, and it was 2 pixels before, and now you've got to increase the minimum size of the parent widget. So that requires a fit. We re-implement the init method to perform some layout initialization. In this case, we're initializing the dataset values to the current direction and alignment for the box layout, and then we just call the superclass init. Next, we have the 3 methods: attach widget, move widget, and detach widget, which were defined by the parent panel layout class, or the base class of this class, and we completely override them. Notice that there's no call to super here in either of these, or any of these, I should say. So we completely re-implement how attach widget, move widget, and detach widget works, because we've got more stuff that we need to do, or I should say, not necessarily more, but different stuff. If we look at panel layout, and we look at, for example, attach widget, one of the things that we did is we looked up the sibling node reference for the thing that we're, we looked up the node which belongs to the sibling widget next to which we're inserting, because when we call the DOM nodes insert before method, it requires that reference node so we can insert it into the actual internal doubly linked list of the DOM tree at that location. And so what this method is doing on the base class is ensuring that the order of the DOM nodes in the order of the nodes in the DOM matches the order of the widgets in JavaScript. And that's important because we're using CSS to lay things out. It's not important for a box layout because since we're using absolute layout, the DOM actually doesn't care about the order of the sibling widgets. We're computing the position that they should be in absolute terms, all in JavaScript. So we don't actually have to look up the sibling node for box layouts or for split layouts or anything like that. They just need to be children of the correct parent, and we can compute where they're supposed to be laid out ourselves. So we always just do the cheap way out, and we just append it to the end of the parent. But what we do have to do is keep track of the positions of the layout items and of the sizers for those widgets appropriately. So when we attach a widget, that means this gets called by the parent class when a new widget is inserted into the layout. And so here's what we have to do. First, we have to insert at the appropriate location a new layout item, which is going to manage that widget. And we also have to insert a box sizer at the appropriate location. That's also going to represent the size of that widget. Then we have similar logic to the base class where if the parent's attached, we tell the child widget it's about to be attached. Then we add it to the DOM, and then we have to check again to see if the parent is still attached. And if it is, we tell the child widget that it's been attached. So we still have to do that same logic that we did here in the base class. We have to re-implement that because now it's our responsibility to send that message. Once we're there, we go ahead and tell the parent that we need to fit itself. So we send it, post it a fit request message. If we looked at the base class, layouts being handled by CSS. So when we move a widget, first we have to tell it it's about to be detached. Then we have to remove it from the DOM. Then tell it that it's been detached. Then look up the new sibling reference. Then go through this whole you're about to be attached, attach it, tell it it's been attached. We have to go through all of that noise again because if we recall, that's how a lot of browsers are actually implemented. I should say, not all of them, but some of the browsers, if you move a DOM node in the DOM, it's actually implemented internally in the browser by removing that DOM node from the tree and then reinserting it, which, depending on what mutation observers you have installed in the DOM, could trigger those mutation observers, or it may not. So rather than have behavior that varies between browsers, we've implemented move as a remove plus an insert because that behaves the same across all browsers, even in the presence of mutation observers. So that's why this base class method is implemented that way. Now, when it comes to a box layout, again, we don't care about the position of the DOM nodes in the tree. So we don't care. We don't actually have to detach. We don't have to move anything in the DOM. We don't have to send any messages. We don't have to do anything. All we have to do, we don't have to do anything to the DOM. All we have to do is move the layout items and move the sizers in the array, which is a very efficient operation, and then tell the parent to relay out its children. So in this case, when we're moving a widget, the child widgets don't care. They don't know. They don't know that they've been removed from the DOM. They haven't been attached or detached. For them, it's all the same. And so this is a much more efficient operation in a box layout than it is in a panel layout. Okay, the detached widget method is pretty much the inverse of attached widget. So I don't think I need to go over it. We're removing it. We're removing all of the state that's associated with that widget, sending the appropriate messages, disposing of the layout item because we're not going to use it anymore, and then telling the parent to fit itself because we removed the child, so its size limits have probably changed. And then we have to do a few more things. We've got a few more methods that we're going to override a little bit because we need to implement some behaviors. We should implement some behaviors based on some optimizations that are made later on in this class. And so I'm going to skip these right now. On, before show, before attach, child shown, child hidden. I'm going to skip those and I'm going to come back to them later and show you why we implemented them, and it will make more sense. Okay, so we're implementing a layout that takes control over positioning the child widgets on the page. That means it needs to be it needs to respond to being resized, or for more specific terms, it needs to respond to its parent being resized. And if we recall, in the base class here, we've got, this is the abstract base layout class, which is the base of all layouts. It's got this process parent message, which gets called by the parent widget whenever the parent receives a message. And that allows the layout to respond to messages that are received by its owner or by its parent widget. And the most common one that's received and processed in terms of number of times it's called, during the application is going to be the resize. That's why it's first, so it can be handled in the first, the first comparison check. What it does is it calls the protected on resize method of the layout, which by default is a no-op. It's an empty method. So the first time it's actually used for something real is in this box layout class. So whenever the parent widget is resized, this method is going to be called, and this allows the layout to actually respond to that parent widget changing size and allows it to compute all of the new space requirements for the children and update all of their sizes. So the first thing it does is it checks to see if the parent is visible. And if the parent is not visible, it doesn't make sense to do any work. So where this might happen, for example, is if we, in this place where we've got a dock panel or something like that. So this trillion row and column tab right here, for example, is not visible when its tab is not selected. So that is visible check will be false. So it doesn't make sense for a layout on that widget to be doing anything when I'm resizing this one right here because it's not visible. So why would we do any of that extra work? So that's the first thing it does, is check to see if the parent's visible. If it's not visible, it doesn't do anything. But what that does mean is that it might have been resized while it wasn't visible. So when it becomes visible, we need to make sure that we do an update. So now we've got here this on before show. This is where we start making use of those lifecycle messages that get sent to the parent. If it was ever a question of why we would use these messages, here's the example of why we would use it. So in the case where, hey, this parent widget's about to be shown on the screen again, we might have been resized. We need to make sure that all of the child widgets are positioned in the appropriate place. So we need to update itself. And that needs to happen before it's actually shown. So posting a message on the before show is totally fine. We'll process that message before the widget is actually visible on the screen to the user. Okay, so if the parent's visible, then we actually need to update all of the children based on the current width and height of that parent. So we call into this private method called update. We'll get into that just a little bit later. But the other time that we need to call this update method is on response to an update request. So notice this naming convention. On update request, we call update. On fit request, we call private_fit. I use that in lots of places. It just so happens that the logic that we use for an update request, meaning to update the position of all of the children, is the exact same logic that we use on a resize because we have to update the position and sizes of all of the children. The only difference is that on a resize, we might know the width and height of the parent. On an update request, we don't know the width and height of the parent because you're just telling, hey, use its current size or figure out what its current size is and use that as appropriate. If we also recall, this resize message in the base widget class is if you don't know the width and height of the current widget, you can pass -1, and that's an indication that says, hey, you've probably been resized, but I don't know what your width and height is, so if you need it, you're going to have to read it from the DOM. We try not to do that. We try not to read from the DOM. We don't have to because it can cause reflows if you mix reads and writes, which are inefficient for the browser to deal with, but sometimes it's unavoidable. So case in point, when we're just calling an update request with no context, we're going to need to read the current width and height of the parent, but sometimes we don't have to. So we can reuse this single update method. We just have to properly handle the case where we know the width and the height versus when we don't know the width and the height. Then we have a message handler that's invoked on a fit request message. And if the parent is not attached from the DOM, we don't have to do anything. But if the parent, because if it's not attached from the DOM, none of the sizes that we try to read from the DOM will be correct anyway, so that doesn't matter. But if it is attached to the DOM, we go ahead and compute its minimum maximum size. Before Jason asks, I probably at some point considered whether I also need to check whether the parent is visible here. And I seem to recall going through that mental process at the time, and I don't recall why I chose not to check whether it's visible at the moment, but I probably had a good reason. But nevertheless, what this does mean is that if the parent is not attached, then we skip this operation, which means that when the parent becomes attached, we actually have to do that operation to make sure that we're up to date. So this is why we have this on before show handler and why we have this on before attached handler, which does these things because we're making these optimizations right here on resizes and updates and fit request messages to not do anything if it's not necessary at the time. Okay, the last two methods are fit and update. I believe it's the last two. Yep, and then we just have a bunch of private state, which holds the state of the layouts. And then we have a bit of box layout namespace, which defines our direction types and the alignment types and the options types. So let me go over this public interface here, and then we'll get back to the those two private methods for doing that, actually doing the fit and the update. So we've got the type alias, which defines the box layout direction. Box layout can do things left to right, right to left, top to bottom, or bottom to top, which is more flexible than most toolkits you're going to find. Most toolkits, you'll get a box layout and they'll do things either vertically or horizontally. And it's up to you to order your children correctly in those. If you wanted to try to do like a bottom to top orientation or something like that, you kind of have to mess with the order of your children in order to do that. The box layout will just do it for you based on the layout direction. Then we have a type alias for the box layout alignment. So again, if you've got extra space that's not all taken up by the children, you can either align all of the children to the start of the layout, you can center them in the layout, you can align them to the end, or you can distribute that space equally between the children, which is the justify mode. Then you got the options for initializing the layout. Obviously, you can specify the initial direction, alignment, and default spacing, or fixed amount of spacing between the children. This is a minimum amount, so it will always at least be this much. If you've got an alignment which is set to justify, then you might get more than that if you've got extra space to distribute between the children. Then you have some attached properties, which allow you to define the stretch factors for your widget. This basically is how you control how much siblings expand or shrink relative to their other siblings in the layout to adapt to that amount of space. So as I remember, if I align all these things here, so we basically have a horizontal box layout here. As I resize the browser window, we see that the children are expanding and shrinking at more or less the same rate, and that's because they all have a stretch factor of 1. They have the same stretch factor. If I gave one of these a stretch factor of, let's say, 2, then as I expanded the window, it would grow at twice the rate of the other ones, of its other siblings. And then we have one more property, which is called the size basis, and this is the initial size basis for, this allows you to set basically the size you would like the widget to be when it starts out. So let's say that the preferred size of some widget might be 240 pixels and another one might be 320 pixels, and you're laying them out in a space that's 700 pixels or something like that. We're going to get the box layout algorithm is going to try to get your widgets as close to that size as possible, if subject to the constraints of your minimum maximum sizes, the allocated space, and all that other stuff that goes into it. It's basically like, hey, try to make it about this size, and it's going to do the best job that it can of trying to do that. Okay, so going back up to the first private method here is fit, which fits the layout to the total size required by the widgets. So what this fit is actually doing is it's going to compute the required minimum sizes, both in width and height, that's needed to fit all of the child widgets into that space, subject to their minimum widths and heights. And so the first thing we need to do is compute the visible item count. And so in this case, if we recall, the items underscore items array is an array of layout items that are wrapping those widgets, which provides us with a bunch of convenience functionality. So we need to compute how many visible layout items there are. And a layout item is visible if its underlying widget is visible, or I should say rather, is not hidden. And the reason we do this is because the box layout ignores widgets which are hidden. So if you've got, let's say, a box layout and you've got a bunch of children in it, and you pick out, child number 3, and you call .hide on that child, it should disappear from the page, and the space that it was occupying should be consumed by the other sibling widgets. And that's exactly the behavior we've implemented here. And we do that by simply ignoring hidden children. They simply do not factor into any of the computations. And you'll see that dynamic behavior. For example, let's say you've got a box layout that's got 4 children in it. One of them is hidden, and you've shrunken that box layout to the minimum size necessary for all of those children, and then you show that hidden child. That box layout will expand because now it requires more minimum width to show the 4 children instead of the 3. So all of that behavior is dynamic and propagates throughout the entire layout tree in Phosphor. First thing we do is we compute the amount of fixed space that's necessary for the visible items. And internally, the terminology that we've used here is the fixed space is the amount of space that doesn't change when the box panel itself, or the parent widget of the box layout, is resized. And in this case, the only thing that's fixed is the spacing. So however much fixed spacing you have between the children times the number of visible children minus 1. So if you've got 2 visible children and you've got 5 pixels of space between them, then the fixed space is 5 pixels. And the reason we've done this here, or this computation here, is we need to keep track of this because the box engine has no concept of space between widgets. If we recall, all it handles is box sizers, which is one next to another. It's got no indication of spacing between these box sizers or anything like that. But that's okay because we can keep track of that ourselves by just adding it or subtracting it from the totals as necessary. So first we need to compute the amount of fixed space that we're going to have in the layout. The next thing we do is to set up the computed minimum sizes. So first we need to check if we've got a horizontal orientation or horizontal direction. So this would be left to right or right to left. And then we compute the minimum width and the minimum height as appropriate. So how do we compute the minimum sizes? Well, the minimum width currently, this is, we're going to add to these, but to start out is if we've got a horizontal orientation, then the minimum width is the fixed spacing that we need. Otherwise, the minimum width is 0. And if we've got a vertical orientation, it's the same kind of logic. All right, so we iterate over all of our layout items. Then, if a layout item is hidden, it should consume 0 size. So what we do there is we just set the sizers, minimum size and maximum size to 0, just so basically the box engine ignores it in the layout computation as well. If the item is hidden, that's all we have to do. We can step to the next item. Otherwise, we need to compute the minimum and maximum size, basically the size limits for that particular item. And so when we call fit on a layout item, what that does is it basically asks, queries the DOM for the current size widget or size limits of that widget's node, and then updates its internal state. So this right here is doing a read from the DOM. And that means whenever we do a fit, we're going to do a read from the DOM, then we're going to follow it with a write later on and an update. And so we're going to mix reads and writes when we do a fit. So it's a more expensive operation. You don't want to necessarily do it every time something is resized, which is exactly why we've separated the logic from fit from the logic of update. If you recall that fit requests are things that go from the bottom of the tree up to the parents. So once you compute the minimum and maximum size of a child, then its parent has to refit. It computes its minimum maximum size, then its grandparent has to do it, and so on and so forth. That goes up the tree. Resizes go down the tree. You resize your window at the top level. Now you've got some new amount of space that has to go down to these children, then they can allocate that space to their children and so on. That goes down the tree. That resize action should be efficient because it happens all the time, and it happens in response to the user moving their mouse. So it should be extremely fast. So really all it should be doing as much as possible is writes to the DOM. It shouldn't be doing any reads from the DOM. So as much as possible, we limited the reads from the DOM to the fit methods, which go up the tree, and they can be expensive, and we do all of our writes in the update method, which goes down the tree. Okay, so we compute the size limits of that layout item by calling its fit method, and then we update the size basis and stretch factor for the box sizer for that, and then we update its minimum and maximum sizes. So this loop is basically extracting information from the layout item and applying it to the box sizer that's going to represent the sizing information for that layout item. At the same time, we're also leveraging that computed minimum width or minimum height that's appropriate and updating the computed minimum width and minimum height as appropriate. Now, if we've got a horizontal layout orientation, then the minimum width is increased by the minimum width of each item, but the minimum height is only the maximum of whatever the current minimum height is and the item's minimum height. So that makes sense, right? If you've got a row of widgets, then the total minimum width of that row is going to be the sum of all the minimum widths of the children, but the minimum height of that row is only going to be the tallest of those particular items. So it's a max operation, and then you can, flip that logic 90 degrees for vertical orientation. But what that does mean is, let's say you've got one particular child widget who has a minimum height that's much taller than all of the other ones. So now you've got this like vertical space in your box that you need to deal with somehow, and you might want to position one of those children, vertically, either leading, trailing, or in the center of that space. Well, if we recall, I believe the layout item does that for us. There's a property for that. I thought there was a property for that. It's an attached property, I believe. Yes. So on layout, there's a horizontal alignment and vertical alignment property that it's an attached property that you can assign to widgets. And what the layout item will do is, given that alignment, the vertical alignment and horizontal alignment, it will make sure that any of that extra free space that's computed that you're trying to assign to that widget that violates its maximum sizes is allocated fairly, either left, center, or right, or top, center, and bottom as appropriate. So that takes care of initializing the sizers. Then what we need to do is compute what we call box sizing of the actual parent node. And so this consists of the padding and the border of the parent, with the CSS padding and the CSS border that's assigned to the parent. So that can be specified by the user in CSS. We have to basically read that from the DOM, and I'll show you where that's done. If we go back to DOM utils, we've got this box sizing function, which will read all of this computed style information that's including the border, all of the border widths, all of the padding for the top, left, right, and bottom, and it'll return to you an object which has all of that individual information as well as the sum of that information. And the reason for that is that you've got this size that's being given to the parent, but from that size, we need to subtract the size of the borders plus the sizes of the padding to get the effective size that we have to actually lay out the children. So when you're thinking about this, let's say that you're the grandparent of some widget, or you're the parent of some widget, and you've computed that it should be 640 by 480 pixels. So you tell it, you size it to that. Now you don't know, as the parent of that widget, what its padding or what its border is defined as in CSS, nor do you care. You're just like, hey, make yourself 640 by 480 pixels. That widget itself, though, if it has a border and if it has padding, doesn't actually have 640 and 480 pixels to lay out its children, because you need to subtract the border and the padding from that. And so that's what the logic here does, is it's computing this up front in the fit method. It's basic, and then it's storing it as appropriate to compute the actual space that we have to lay out those children, because it needs to take that into account. Okay, so we get the box sizing and add it to the computed minimum size. So what that results in is the actual new minimum size that's required by the parent. So if the children need a total of 400 horizontal pixels, and the parent's saying, well, wait a second, I have, a 10 pixel border and 10 pixels of padding all the way around, that's an extra 40 pixels total in the horizontal direction. Now I need at least 440 pixels at my minimum size in order to display all of this correctly. So the box layout's doing that computation for you as well. And we set a dirty flag to ensure only a single update occurs. And the reason for that is that the next thing that's going to happen is we notify the ancestor it should fit immediately. This may cause a resize of the parent, fulfilling this required update here. So let's read that again. So what's going to happen here is this parent widget has its own parent. Since we've changed the minimum size of this particular parent widget, its parent widget now needs to update its own computed minimum sizes and relay out its children. So it has to go through a fit process. So we send it that fit request message. And notice we send it, we don't post it because it needs to happen immediately. What that means, since this is a synchronous call, the result of that parent doing its fit might be that it tells our current parent widget that it needs to update itself. If that happens, then we only want to do the update once. If we don't get that that update request message, we need to make sure we send it to ourselves because we've changed our minimum sizes. That may cause our computed sizes or whatever to change. So we have to lay out our own children. We need to update our children. So we need to do an update. So what we do is we set a dirty flag and we set that to true. Then the first thing we do in our update method is set it to false. What that allows us to do is between setting it to true and this message finished, the processing of this message being finished, that dirty flag, if we've updated, will be set to false because this whole block is synchronous. If that hasn't happened, so if the dirty flag is still true, then we need to update ourselves, and so we send an update request, and it needs to also happen immediately. So this is basically just a little flag that we flip true and false to make sure we're only doing one update in response to that because there's no need to do more work than is necessary. All right, that was a bit of a tricky logic method. Are there any questions to that? I don't know that I did a great job explaining it, so please ask questions if there are any.
So this only works if the parent sends the update, not if it posts the update.
Correct,
right?
Because posting would be asynchronous, so nothing would happen here. This would be basically, it would post it, to the event loop, and this would return immediately. And so this .30 would always be true if this was post message instead of send message.
Right, or if the parent posts an update message. So if the parent calls a widget.update that sends a message, doesn't post it?
No, it posts it, which might happen. But it probably won't happen because the parent doesn't call widget.update. If it's an absolute, if it's a layout that's doing absolute positioning, it's going to call the layout item.update, which is synchronous.
Okay.
The most likely to occur thing is this .dirty will be false. That's the most likely to occur because typically if you're using a box layout that has a parent, it's also going to be some form of absolute layout, but it might not be. So it's just a check that we're basically just covering all bases there. Okay, last method of this class is the private update method, which updates the layout position and size of the widgets. And we say, the parent offset dimension should be -1 if unknown. So we're using the specific terminology here of offset dimensions and offset width and offset height because that's what's defined in the DOM spec as the width of the node, including its border and padding. So there are different widths and there are different heights that some don't include the border, some don't include the border or the padding, but the offset width and the offset height does include the border, it does include the padding. And that's why I've used that terminology here rather than just simply width and height. It's just to be as explicit as possible. So this is the width and the height of the parent, including its border and including its padding. So first thing we need to do, set the dirty flag to false. The next thing we need to do is compute how many how many layout items are visible, because that's, we need this count to begin with. If there are no visible layout items, then nothing needs to be done. We can bail early. If the offset width or offset height is -1, we need to go ahead and do a read from the DOM. This is unfortunate. It might cause a reflow, which is why, as much as possible, if you're sending resize messages around and you have somehow computed and you already know what the width and the height of the thing is that you're resizing, you should include that information. Otherwise, it's going to have to be read from the DOM at some point. And so that's where this is done right here. If somehow we haven't already computed the box sizing of the parent, we go ahead and compute it now and we cache it. It is, if we recall, should be, yeah, right here. It is refetched anytime you call fit on a parent. So right here is when we do a recaching of that box sizing. But when we do an update, we only read from the DOM if necessary. So it's read once and then cached until the next fit. Then we actually compute the layout area adjusted for the border and padding. So the top and the left, these are the origins of the box. That's going to be these are now, I'm now converting into basically CSS coordinates. So it's funny, the offset width and the offset height in CSS includes the border and the padding, but the origin of the 0, origin of the parent's local coordinate system is at the intersection of the border and the padding. So you can't actually lay out anything in the border space, but the border space is including on the offset width. So the actual origin where we want to start laying out children is the padding top and the padding left. So if I just, let's say you've assigned some padding, to a parent widget, and I just place, and your padding's 5 pixels, top and left, just pick a number. But I tell a child widget in absolute layout terms to position itself at 0, 0. The padding gets ignored by CSS. So when you're using absolute layout, if you want to obey padding, you have to do it yourself manually. And so that's what this computation does right here. So we start the origin, the top and the left origin, at the padding boundaries that's specified by the user in CSS. So that's just one of those weird CSSs that, again, Phosphor is dealing with for you. Then we compute the width, and the width is going to be available width that we have to lay out our children is the offset width and height minus the horizontal sums of padding and border. Then we distribute the layout space and as appropriate, or adjust the start position, if you will. So this is all based on the direction. So left to right, we need to, if we recall when we were going over the box engine module, Darian asked the question whether you can favor distributing space to the leading sizers or the trailing sizers. And that might call into question how you need to call this function based on whether you've got a left to right or a right to left layout direction. And what I told Darian was that it doesn't actually matter whether you're laying out left to right or right to left. The algorithm for calculating the available space distributes everything fairly, looking at the entire array of sizers at the same time. So an interesting property of that is that for a given amount of space, if you have your children in a particular order and you reverse their order, they'll end up with the same allocated space, no matter no matter the order that they're in, as long as they're in the same, relative order and have the same stretch factors and all of that. So when we compute left to right calculation versus the right to left calculation, it's the exact same call. And the only reason that I don't have this case left to right and case right to left combined together is because we need to adjust the starting position of the top, or the top position the top starting position or the left starting position, based on whether we're doing a reverse layout or a normal layout. So it's a little bit of a tricky mental exercise, but when you step through this, and if you were to step through this algorithm and you would write in a way that's sort of naive, where you handle each case individually, you're going to notice that there's a lot of common code that can be refactored out and shared amongst the various cases. And so what we're doing is just leveraging the fact that if we're doing a left to right layout versus doing a right to left layout, the widths, the computed widths of all of the children are going to be the same, whether we lay them out left to right or whether we lay them out right to left. The only difference between the two is our starting position of where we start the position of each child, and whether we increase our running position based on the child width, or we decrease our starting position based on the child width. And we'll kind of see that in the next, how we account for that. That's why you see the commonality between these various clauses of the calc function. Okay, then we need to account for justification and alignment. So if we recall, when the box layout calc function is called, it returns the amount of space that is remaining. Let me pull that up again so we can look at the documentation. So we go to Box Engine. And it returns the delta between the provided available space and the actual consumed space. The value will be 0 if the sizes can be adjusted to fit, negative if the available space is too small, and positive if the available space is too large. So if this function returns a positive number, that means we've allocated more space than can be consumed by all of the child widgets. If that happens, we need to account for the alignment of the children. So if there's extra layout space and we've got an alignment that we care about, if we're aligning at the start of the layout, we don't care. If we're going to center the children in that space, then we need to account for that. Or if we're going to position all of the children at the end, we need to account for that. And if we're going to justify, then we need to split up that extra space by the number of visible children. And so that's what we're doing here. We're basically switching through this and figuring out how we need to handle our extra space and any additional offsets for the running position.
I'll just add here that Flexbox has a few other possibilities for how to distribute that space if we ever need another possibility. There's a few other in the Flexbox standard.
What are the other ones? I know it does some wrapping, which we don't try to do here. I would write a different layout if I was going to wrap stuff because of.
Yeah, this is without wrapping. There's space between. There's
justify.
There's space between, space around, and space evenly.
Yeah.
Yeah.
Well, what's between space evenly and space between? What's the difference between those two?
Space between items are evenly distributed in the line. First item is on the, well, if there is wrapping, blah, blah, blah. Space around, items are evenly distributed in the line with equal space around them. And space evenly, items are distributed so that spacing between any two items is equal, including the space to the edges. So one variant, for example, is to say everybody has a buffer of space around me. So between items, there's twice the amount of buffer space. And another is, I think, what you're doing with justify, which is visually there's equal spacing between the edge of the first item, between the first item and the second item, et cetera. Anyway, there's a couple other possibilities. I don't know how useful they are in practice. I think you've covered the main ones that you would see in practice.
Yeah, yeah. Maybe there's some other little small. I'm not opposed to adding another case if we come up with a good use case for some other way to distribute that space. It's easy enough to add, and it's.
I was just pointing out that.
Change.
Yeah, I was just pointing out that there was at least use cases that were proposed and implemented in the standard, in the Flexbox standard, that presumably have some use out there if it ever comes up and is useful in Phosphor, you could put it in.
Yeah. Okay, once we compute all that, now we can actually iterate over the layout items and actually do the actual positioning and sizing of those particular widgets. So first thing we do is we ignore the hidden items. Then we look up the box sizer for that particular layout item, and we fetch its computed size. Then we go ahead and we, in this case, this is a bit of a concession to practicality over, convenience. Technically, this dot underscore direction is not going to change for the duration of this loop. So I could have put this switch case on the outside of this for loop, but then I would have a bunch of cases with repeated logic of for loops in them. So this seemed to be the cleaner way to write this function, if not the most efficient way to write this function. There is a possibility that some of the advanced JITs and JavaScript engines could do some basically loop invariant code hoisting and hoist out this switch case statement for me automatically. And whether it's being done or not, I don't know. But this is fast enough in practice that it doesn't really matter. So yeah, if you're going to be a purist, this switch should probably be outside the loop rather than inside the loop. But this kind of cleaned up was the shortest way to write the function. So for each item, we need to take care of which way we're doing the layout, whether it's left to right, top to bottom, right to left, or bottom to top, because that is basically, we change where we apply that offset and whether we're adding the offset or whether we're subtracting the offset, minus the computed size, minus the extra space, and all that kind of stuff. But this is basically just running through the math logic. It's iterating one at a time. The easiest to understand is left to right. So what we're doing as we're iterating over all of these items, we take the current position, the current running position, the left position, plus whatever the offset is that we're computing. We updated so that's the left position of the box. The top position of the box is always the computed top. The size that it gets allocated to it is its computed size plus any extra space that we've given it. That's, and the extra space is what's being distributed as extra space as computed in this block right here. And then it's the height is the computed height of the height is the computed height of the parent. And then we basically update the left edge for the next box. So that's going to be, we have to add in the size of the widget plus its extra spacing plus the spacing between items. And so basically what we're doing is we're stepping from left to right, computing what the current left position is, updating that item, and then computing the next left position, and then continuing on through the loop. And then if we recall real quick, let's look back at this update method on the layout item. What that does is take the geometry that it's been given, it clamps it to the computed size limits of the widget, and then it adjusts for any horizontal or vertical alignment that's been specified on those attached properties. Then it keeps track of whether or not it's going to actually resize the widget, and it updates the absolute styling position for that widget. And if it has detected that it's resized the widget from its last size, it will send that resize message to it. So that's basically that is the general logic for implementing an absolute layout. As we'll see, the next class I'm going to go over, I guess next week, is going to be well, I guess I'll do box panel, but then the split layout and split panel are very, very similar to box layout and box panel. There's a couple of adjustments to handle the interactivity with the mouse and the resizing handles and whatnot, but the overall layout logic is extremely similar to this.